Right. Welcome back, everyone. It's Season 1, Episode 3 of Decoding Quantum Computing. And we're still part of the Curious Decoder podcast, of course, where we just dive into all these complex topics, try to make sense of them with hopefully a bit of fun along the way.
Yeah, that's us always trying to answer that question, what does that even mean? While having a bit of a laugh.
Absolutely. And as you know, we're spending this whole season really getting to grips with quantum computing.
Yeah, a proper deep dive into the quantum realm.
And today feels like, well, a pretty big step, doesn't it? Because we're going right to the core. We're talking about the real building blocks of quantum computers, the heart of the matter, so to speak. Today's deep dive is all about meet the Qubit, the heart of quantum computing. This, my friend, is where things start to get really quantum.
They do indeed. You see, when you think about your typical computer, it's all built on bits, those zeros and ones.
Right. The simple on or off, yes or no of it all.
Exactly. But quantum computing, well, it introduces something much more, let's say, flexible.
Yeah, flexible is a good word for it. It's like taking that on-off switch, that binary choice of a bit in a regular computer, and suddenly it can be both on-ish and off-ish at the same time. Bit of a mind bender, that one.
That's the Qubit for you. It's all about that expanded potential. So our mission today is pretty straightforward. We want you to really grasp what a Qubit is, how it's related to those bits we all know from our phones and laptops, and most importantly, why this seemingly small change, the shift from bit to Qubit, unlocks these almost unbelievable computational powers that classical computers, well, they just can't touch. And of course, we'll do our best to explore all this without getting too lost in the, shall we say, denser mathematical thickets.
Right. We don't want anyone's eyes glazing over too much. Now, to really appreciate why the Qubit is such a huge leap, I think it's helpful to take a step back and consider where computing started. We often hear about Alan Turing, and for good reason.
Oh, absolutely. Turing's work is foundational.
Yeah, his concept of the Turing machine, this idea of a universal algorithm, well, it laid the groundwork for practically everything we do with computers today.
Back in the 1930s, Turing was grappling with some pretty abstract questions about the limits of mathematics. He was trying to figure out what it meant for a problem to be solvable by a step-by-step process. Computable, in other words. He wanted to know if there was a universal method to solve any mathematical problem that could be solved in this way.
Sounds quite the brainy endeavor, doesn't it?
It was. But in trying to answer these big abstract questions, Turing was forced to define very precisely what an algorithm is.
Yeah, he had to break down the very essence of computation.
And that led him to describe his famous Turing machine. It was a theoretical device that could, in principle, perform any algorithm you could think of. The idea was that you'd feed the machine a set of instructions, a program, and it could then carry out any computational process. It was a monumental idea.
It was a real turning point, wasn't it? I mean, before Turing, the idea of a single machine that could carry out any computational process, given the right instructions, well, that was quite revolutionary.
It was. And it's the fundamental idea behind every digital computer we use today.
But here's where things get even more interesting. A few decades later, physicists like David Deutsch started to look at this from a slightly different perspective. In 1985, Deutsch made a really key observation. He pointed out that every algorithm, no matter how abstract it seems, is ultimately carried out by a physical system.
Right, whether it's someone doing calculations by hand, an old-fashioned abacus, or the chips in our modern computers, they're all physical systems.
And Deutsch took this idea and asked a really profound question. He asked, is there a single universal computing device that can efficiently simulate any other physical system?
Now that's a fascinating question. If such a device existed, it could perform any algorithm by definition.
Precisely, because any algorithm needs some physical hardware to run on.
And Deutsch realized that this way of thinking had a real advantage. Instead of relying on intuition about what an algorithm is, as Turing had to do, you could potentially use the laws of physics to prove that your device was truly universal.
So you're grounding your concept of computation in the fundamental laws of the universe.
Exactly. But this leads us to a pretty fundamental problem with classical computers. When we look at them this way, through the lens of physics, Deutsch, along with other brilliant minds like Manin and Feynman, they all realize that our everyday computers, the ones based on Turing's model, they hit a wall when they try to simulate quantum mechanical systems.
They get incredibly bogged down, don't they?
They do. Trying to simulate the quantum world on a classical computer, it's a bit like trying to describe a curved surface using only straight Lego bricks. You can do it, but it takes an astronomical number of bricks. It gets incredibly complex very quickly.
And all that complexity translates into time and computational resources. It just becomes very inefficient.
And this inherent difficulty, this bottleneck in simulating the quantum world on classical computers, well, that's what gave birth to the idea of a quantum computer.
Right. The thought was, if the universe at its most fundamental level operates according to the strange rules of quantum mechanics, maybe a computer built using those same rules would be a far more natural and efficient way to simulate it.
It's like using the universe's own language, so to speak.
Precisely. So in a way, quantum computers aren't just a clever invention. They're a response to a really deep question about the nature of reality itself, the possibility of building a truly universal simulator.
It's a beautiful idea.
It is. And that brings us directly to our star of the show today, the Qubit. Let's get properly acquainted. We all know about bits, those zeros and ones, the fundamental units of information in classical computers. They're physical things, right? An electrical charge, a magnetic orientation.
Absolutely. A bit exists in one of two well-defined states, 0 or 1.
Now the qubit, that's the fundamental unit of information in a quantum computer. And while it has some similarities with the bit, there's a crucial difference.
The key difference is in its state. You see, unlike a bit, which is restricted to just 0 or 1, the state of a qubit is described by a two-dimensional vector.
Okay, now I know that the word vector might make some people's eyes glaze over a bit,
Yeah.
but don't worry, we're not going to get too deep into the mathematical weeds here.
Right. The main thing to grasp is that this two-dimensional nature gives the qubit a much richer set of possibilities compared to a simple bit. It's like going from black and white to a full spectrum of color.
And just like you don't need to know the exact type of transistor in your phone's processor to make a call, we don't need to delve into the physical details of what a qubit actually is right now.
Right. For our purposes, it doesn't really matter whether it's an electron, a photon, or an atom.
Exactly. What matters is the abstract mathematical object that describes its state.
Think of it this way. A bit is like a light switch that can be either on or off. A qubit, on the other hand, is more like a dimmer switch.
Ah, I like that analogy. It's not just fully on or fully off. It can be somewhere in between.
Precisely. And this in-betweenness is represented by its position in state space, which is this two-dimensional vector space where all the qubit's possible states live.
It's like a compass needle. A regular compass can only point north or south, but a qubit's needle can point anywhere on a 2D plane.
Now, to make things a bit more concrete, let's connect these qubits back to the bits we're all familiar with. There are two special quantum states that correspond directly to the 0 and 1 states of a classical bit.
Right, so we have our good old 0 and 1, but they've got a bit of a quantum makeover.
Exactly. The quantum state corresponding to 0 is written as, and this might look a bit odd at first, a 0 with a sort of bracket around it. It's called ket 0, and it looks like this. 0 angle.
And mathematically, this ket 0 is represented by a column of two numbers, a vector, with a 1 at the top and a 0 at the bottom. It looks a bit like this. Begin matrix 1 matrix.
And similarly, the quantum state corresponding to 1 is written as ket 1, like this. $1 angle. It's represented by a vector with a 0 at the top and a 1 at the bottom. Begin matrix 0 around.
Now these ket 0 and ket 1 states have a special name. They're called computational basis states.
Think of them as the fundamental reference points in the qubit state space. They're the quantum equivalents of the classical 0 and 1.
And that strange notation we mentioned, the dollar angle wangle symbol, that's called ket notation. It might look a bit strange, but it's just a shorthand way of representing a quantum state.
Exactly. So when you see something like 0 or $1 angle, just think of it as a single symbol that stands for a specific quantum state.
And that state is represented mathematically by a vector, as we just saw. The key point here is that a quantum computer can manipulate these ket 0 and ket 1 states in ways that are similar to how classical computers manipulate their 0s and 1s.
So there's a connection to the familiar world of bits. But as we'll see, qubits can do so much more.
And that brings us to the truly mind-blowing part of the qubit, its ability to be in states that are not just ket 0 or ket 1. These computational basis states, they're just two specific points in a vast landscape of potential states.
And this is where the concept of superposition comes in. This is where things get really interesting. A qubit can be in a superposition, which means it's in a combination of both ket 0 and ket 1 at the same time.
Hold on, both at the same time. How can it be in two states at once?
Well, that's the quantum magic, isn't it? Mathematically, we write a superposition like this. alpha wrangle plus beta 1 wrangle dollar, where alpha and beta are complex numbers. Don't worry too much about the complex numbers for now. Just think of them as numbers that allow us to describe these quantum states.
So a qubit can be a bit of 0 and a bit of 1 at the same time.
Exactly. And the amounts of 0 and 1 are given by those alpha and beta values. For example, a qubit could be in the state 0.16 tangle plus 0.81 wrangle phi.
So it's kind of like a dimmer switch that's not just on or off, but somewhere in between.
Yeah, that's a good way to think about it. Now, you often hear people describe superposition as the qubit being simultaneously in both states. And while that's a helpful image, it can be a bit misleading if you take it too literally.
Right. It's not like the qubit is somehow flipping back and forth between 0 and 1 really quickly. It's more subtle than that.
It really is. The classical idea of simultaneously being in two states doesn't quite capture what's happening in the quantum world. It's a bit like trying to understand how a wave in the ocean works by just thinking about individual water molecules.
You need to look at the whole wave, not just its individual parts.
Exactly. And with qubits, the best approach is to work with these superposition states mathematically to see how they behave before trying to find a perfect analogy in our everyday experience. The key takeaway is that this both-at-once nature of superposition allows a quantum computer to explore many possibilities simultaneously, which is something a classical computer can't do.
Right. It's a massive advantage.
Yeah.
So we have these qubits that can exist in this multitude of states thanks to superposition. But how do we actually do anything with them? How do we manipulate them?
Well, that's where quantum gates come in. They're the quantum equivalent of the logic gates in your computer's processor, the things that perform operations on the bits.
So these quantum gates are the tools we use to control the state of our qubits.
Exactly. And while some of them have classical counterparts, they operate in the quantum realm and can do some pretty extraordinary things. Let's look at a couple of examples. First up, we have the quantum NOT gate, often called the X gate.
The NOT gate, that rings a bell. It's like the classic logic gate that flips a 0 to a 1 and a 1 to a 0. Right?
That's the one. And in the quantum world, it does exactly the same thing to our computational basis states. So if you apply the NOT T gate to a qubit in the state for ket 0, it becomes ket 1, and vice versa.
So it just flips them around. And what happens if you apply the NOT T gate to a qubit that's in a superposition?
Well, in that case, it flips the contributions of the basis states. So if you have a qubit in the state alpha wrangle plus beta 1 wrangle, applying the NOT T gate gives you alpha 1 wrangle plus beta wrangle. The alpha and beta just swap places.
So it's like it's mirroring the superposition.
Exactly. Now, just like many quantum operations, we can represent the NOT T gate mathematically as a matrix. It looks like this. Zex dexters begin matrix, 0 and 1, 1 and 0, end matrix. And applying the gate to a qubit's state is the same as multiplying this matrix by the qubit's state vector.
Right. So the math is there behind the scenes, but we don't need to dive into the details just yet. Now, the NOT T gate is a good example of a quantum gate that has a pretty clear classical analog. But things get really interesting when we look at a gate that's distinctly quantum.
That's right. And a prime example of that is the Hadamard gate, often just called the H gate. This one's a real game changer.
Okay, the Hadamard gate, tell me more.
Well, the Hadamard gate takes the computational basis state, ket 0, and transforms it into an equal superposition of ket 0 and ket 1.
So it takes a definite 0 and turns it into this fuzzy in-between state.
Precisely, and we can write that superposition as frac wrangle plus 1 wrangle. And the Hadamard gate does a similar thing to ket 1. It transforms it into another superposition, which is frac wrangle 1 wrangle.
So it's taking these definite states and putting them into this kind of probabilistic limbo.
You got it. And for a general superposition, like alpha wrangle plus beta 1 wrangle, applying the Hadamard gate gives you a new superposition. Frac alpha plus beta squared to 1 wrangle plus frac alpha beta squared to 1 wrangle. It's essentially a linear transformation of the Qubits state.
Right, so it's mixing those alpha and beta contributions in a specific way. And I'm guessing the Hadamard gate also have a matrix representation.
It does, and it looks like this. 700 frac 1 squirt 2, 711, N1 matrix. And if you're familiar with matrix multiplication, you can see how applying this matrix to the ket 0 vector gives you the equal superposition we just mentioned.
So the math checks out. But what's really significant about the Hadamard gate, what makes it so special?
Well, the Hadamard gate gives our quantum computer a whole new set of tools, a set of operations that classical computers just can't do. It's like giving a chess piece a whole new set of moves.
Okay, I like that analogy. It's like suddenly being able to move your rook diagonally, for example.
Exactly. It allows the quantum computer to explore these computational shortcuts, these paths that are simply not available to a classical computer that can only deal with one bit at a time.
It's like upgrading from a bicycle to a spaceship for certain computational tasks.
Precisely. Now, to really see the power of the Hadamard gate, let's imagine a simple quantum circuit where we apply the gate twice in a row.
Okay, so we take our qubit, let's say it starts in the state ket 0, and we hit it with a Hadamard gate.
Right, and that takes ket 0 to that equal superposition we talked about, Frangle plus 1 Wrangle.
And then we apply the Hadamard gate again to this superposition. What happens then?
Well, if you work through the math, something really neat happens. You get back to ket 0.
Wait, so applying the Hadamard gate twice is the same as doing nothing at all?
That's exactly right. It's like having a quantum wire that just transmits the state unchanged.
So it's like taking a step forward and then a step back, and you end up right where you started.
Precisely. And this illustrates a really important concept in quantum computing called interference.
Interference, like waves canceling each other out.
That's the idea. In quantum computing, the different possible paths that a qubit can take, those paths interfere with each other. And that interference can be constructive, where the paths reinforce each other, or destructive, where they cancel each other out.
And the Hadamard gate is playing with that interference.
It is. It's creating these superpositions where different possibilities can interfere with each other. And this is crucial for many quantum algorithms. They exploit this interference to find the right answer by making the wrong answers cancel themselves out.
That's pretty amazing. So we can prepare these qubits in all sorts of interesting states with superposition, and we can manipulate them with these fascinating quantum gates. But how do we actually get an answer out of this quantum system? How do we make sense of it all?
Well, that's where measurement comes in. Measurement is how we extract information from a qubit, information that we can understand and use.
So it's like looking at the qubit and seeing what state it's in.
Sort of, but it's not quite that straightforward. When we measure a qubit, we're forcing it to choose between ket 0 and ket 1.
So we're collapsing that superposition.
Exactly. Now, if our qubit is in a superposition, say alpha wrangle plus beta 1 wrangle, when we measure it, we don't directly get the values of alpha and beta. Instead, we get a probabilistic outcome.
So it's like rolling a die. We know the possible outcomes, but we don't know which one we'll get until we roll it.
That's a good analogy. The probability of getting 0 is equal to the square of the magnitude of alpha.
Okay, so the bigger alpha is, the more likely we are to get a 0.
Exactly. And similarly, the probability of getting 1 is the square of the magnitude of beta.
So measurement is inherently probabilistic in the quantum world.
It is. And here's a really crucial point. Measurement disturbs the state of the qubit.
What do you mean by disturbs?
Well, it means that once we've measured the qubit and gotten an outcome, the qubit state changes irreversibly. If we get a 0, the qubit state collapses to ket 0. If we get a 1, it collapses to ket 1. And the original superposition, those values of alpha and beta, they're gone. We can't access them anymore. It's like bursting a soap bubble. Once it's gone, you can't get back the delicate shimmering colors that were on its surface.
So we can't just cram a whole bunch of information into those alpha and beta values and then read it all out later.
Unfortunately not. Measurement gives us one bit of classical information, and it changes the qubit state forever.
Right, so it's a one-way street. And this also explains why that normalization condition, alpha 2 plus beta 2, is so important.
It does. That condition basically says that the probabilities of all the possible measurement outcomes have to add up to 1. There's always a 100% chance of getting some outcome.
Right. We can't have a qubit that has a 50% chance of being 0 and a 75% chance of being 1. That wouldn't make any sense.
Exactly. So to sum up, you've now met the qubit, this fundamental unit of information that's far more versatile than the classical bit. It can be in a superposition, this intriguing mix of 0 and 1, and it can be manipulated using these unique quantum gates, like the Hadamard gate, that have no classical counterparts.
And we've seen how measurement, the process of extracting information from a qubit, is probabilistic and comes with this price tag of collapsing the qubit state.
It's a delicate dance between the quantum and classical worlds.
It really is.
Yeah.
Now, this ability of the qubit to be in multiple states at once, to be manipulated in these distinctly quantum ways, well, that's what gives quantum computers their enormous potential to solve problems that classical computers just can't handle.
Problems that would take a classical computer billions of years to solve, a quantum computer might crack in minutes.
And just think about how that simple Hadamard gate can take a definite state, like series 0, and instantly turn it into a balanced superposition, giving the qubits an equal chance of being 0 or 1.
That seemingly simple operation is the bedrock of many powerful quantum algorithms. It's the key to exploring many possibilities simultaneously.
It's amazing to think that something so abstract can have such profound consequences. Now, I know the whole concept of simultaneous states and superposition, it can be a bit mind-boggling, but remember that the true power of quantum computing lies in the math.
That's right. It's the mathematical framework and these non-classical operations that we can perform on these qubits that really give them their power.
It makes you wonder what other amazing things we might discover as we learn to control and manipulate these quantum systems. What other weird and wonderful behaviors might emerge as we start connecting multiple qubits together and applying more complex sequences of gates?
That's a great question, and it's something we'll definitely be exploring in future deep dives. For now, just let this concept of the qubit, this flexible, vector-like entity capable of superposition, really sink in. It's truly the heart of this quantum revolution that's unfolding.
Absolutely. It's the building block of a whole new way of computing. Thanks so much for joining us on this deep dive into the qubit. It's been a pleasure, as always.
The pleasure's all ours.
And if you found this as mind-bendingly fascinating as we do, well, be sure to tune in next time as we continue our journey into the world of quantum computing. Until then, keep those curious minds firing.
Right. Keep exploring.
And don't be afraid to ask those, what does that even mean? Questions.
That's what we're here for.
Until next time, everyone.
See you then.